I welcome you for the course Mechanics of Solid lecture series. And last class we have discussed about three kinds of stresses, and we also had a small short form to remember that is TCS. Yes, tensile, compressive, and shear. Let us see how these three stresses and deformation happens in the larger structures. Before going to larger structures like beams, shafts, and everything, let us see a small simple bars in this lecture series. And what is a deformation in a bar? Yes, before load, the original state, no external forces applied. And whenever there is a tension, axial force pulls, causes elongation. And whenever the axial forces pushes, causes shortening, and we call it as compression. That we have seen in the last class. And deformation is the change in bar's length or shape due to applied forces. Axial load refers to forces applied along its length. So coming to the stress and strain basics, we had a definition in the last class. Let us see the stress, which is force per unit cross-sectional area. Suppose we have a particular bar of length L, and this exposed area is subjected to an external load. This external load will cause deformation, and the force applied on this particular area is that when we divide this force with upon the area, we get the stress, and the unit is Newton per meter square, as we have already seen. And the strain is change in length by original length, and that is the change in length is delta L, and length is L. Since both the numerator and denominator variables are same, we don't have unit for this strain, and it is dimensionless. And Hooke's law behavior, elastic behavior is like within the elastic limit, stress is directly proportional to strain. That is the Hooke's law we have seen in the last class. And to remove the proportionality, we introduce a proportionality constant as capital E. And this capital E is nothing but Young's modulus, that is material stiffness constant. And elongation bar, elastic deformation happens when bar returns to its original length upon the load removal. So calculating deformation of a simple bar, we have a formula as delta L equal to F into L divided by A into E. So the deformation increases with force and length, and but it decreases with a larger area and stiffer materials. That is what we have to understand with this formula. And we have something called as Poisson's ratio. So whenever a bar is elongated along the lengthwise, and we have contractions on the lateral surface, and the lengthwise strain is called linear strain or longitudinal strain, and the lateral surface we have something called as lateral strain. So axial loading causes both elongation, shortening, and lateral contraction or expansion. That is to be understood whenever any object is loaded. And when we have the ratio of lateral strain to the longitudinal strain, we call it as Poisson's ratio. And it is typically 0.25 to 0.33 for metals, explaining perpendicular dimensional changes, and 0.4 for rubber. So rubber has the highest Poisson's ratio. This has to be kept in mind since we use for these things will be asked in our graduate aptitude test in engineering. And coming to the real world applications, we have bridges, columns, and cables. So here we have simple bars concept. Everything will be rectangular geometry or circular geometry. So engineer to withstand complex load and deformations on the bridges applications. And columns, it must resist buckling under compressive loads, and the cables designed for tensile strength and controlled elongation. So the summary of this particular lecture is predictable deformation. Use stress, strain, and Hooke's law for accurate analysis. And governing factors are Young's modulus and geometric dictate stretching or compression. And the safe design is understanding deformation is crucial for resilient structures. Apply these principles for robust and efficient engineering designs. So coming to the mind map of this particular lecture, this deformation of simple bar is branched into fundamental or foundational concepts, stress and strain basics we have seen, and governing laws and ratios, calculation and analysis, where elongation we had a small example to understand, and the design significance for safer design. And in the assessment part in engineering mechanics, assuming a body to be rigid helps to, we have four options. One is accurately predict deformation under load, simplified analysis by neglecting deformation. So increase the strength of the material, allow the body to change shape freely. So assuming the body to be rigid helps in simplifying the analysis by neglecting deformation. That is the right answer for this quiz. And coming to the second one, which one of the following is an example of a deformable body in a real life application? A steel rod elongating under tensile load, a perfectly hard sphere with no deformation, a rigid beam with no bending, an idealized point mass. So these A, B, C, D options, A is the right answer since the steel rod elongating under tensile load comes under the deformable body, and other things are the examples of rigid body. So I hope you understood this simple bars deformation, and the forthcoming topic will discuss about the compound bars. Here is the reference for this lecture. You can go through and explore more. Thank you all.